Welcome to the 7th session of ionic equilibria. In this session, we will be dealing with a particular type of solutions known as buffer solutions. Now, we all know that if we add a base to an acid, naturally the acidity will be decreased, or if I add an acid to a base, the basicity of that base will be reduced. Now, here we are going to see a particular type of solutions in which whether you add small quantities of strong acid or strong base, its pH remains unaltered, and such solutions are known by the name buffer solutions. Now, let us see in detail. Buffer solution, by definition, it is a solution that can resist the pH change. It can resist the pH change with the addition of appreciable amounts of strong acids and bases. Even if you add strong acids and bases to it, its pH does not change. The property by which the buffer resists its pH change is known as buffer action. So, we know what is type buffer, and the resistance of pH change by the buffer, that mechanism is known as buffer action. Now, let us see what are the types of buffer we have. There are two types of buffers mainly, that is an acidic buffer and alkaline buffer, or it is also known as basic buffers. Acidic buffer, as we all know, acid is a solution. When pH is equal to 7, we say that to be neutral. When pH is less than 7, we say that solution to be acidic. When pH is greater than 7, we call that to be basic or alkaline. Now, here I am going to talk about acidic buffers. So, it should come to your mind that it will be having an acidic pH. So, buffers which have a pH less than 7 is known as an acidic buffer. It will be generally a weak acid and its salt. Okay. The salt should be of a weak acid. Now, what should be the salt? Salt forms from an acid and a base, and here it is very important, the base should be a strong base. So, acidic buffer means examples will be a salt formed from weak acid, but the base should be strong. Example is, we are having a weak acid, acetic acid, and the salt should be sodium acetate, where sodium is a strong base, sodium hydroxide, and acetate comes from acetic acid, which is a weak acid. Now, we have an weak acid and a salt. The salt should be something from a strong base, and the acid can be weak. Now, if I take equimolar mixture, what does it mean equimolar? If acetic acid I am taking 1 molar, sodium acetate should also be 1 molar. Equimolar mixture if I take, if it is 2, then the other one is also 2. It will have a pH around 4.76. Now, to this, even if you add small quantities or you can have a somewhat appreciable amounts of strong acid or a strong base, the pH does not change, it still remains at 4.76. If you vary the amounts of acetic acid and sodium acetate, you can have the value of pH to be differing. Next comes the alkaline buffers, or you can call that to be a basic buffer. Basic buffers are those which will have a pH greater than 7. In this case, it should be a mixture of weak base. In the other case, it was weak acid. In this case, it is a weak base and its salt. Salt should be from a strong acid. It is very important. And according to the proportion of weak base and its salt, the pH varies. If I am taking again equimolar mixture of ammonium hydroxide, this is a weak base, and this is a salt. From this chloride ion comes from HCl, this acid is strong. So, weak base and its salt from a strong acid. Okay. Now, again if I take a equimolar mixture of these two, the pH will be 9.25. Here it is the pH is greater than 7 and that gives an alkaline pH. So, such buffers are known as alkaline buffers or basic buffers. Now, what are the characteristics of a buffer? It has a definite pH value, that is, if you take a buffer in a particular proportion, that will be having a definite pH value. The pH remains unaltered even on standing or dilution. You can dilute with water, but its pH will not change. pH remains unaltered upon addition of small amounts of strong acid or strong base. So, these are the characteristics of a buffer solution. Next, we have to find out what is the capacity of a buffer. To measure the capacity of a buffer, like how far it can resist the pH change, is done by a factor known as buffer index, denoted by the letter beta. The capacity of the buffer to resist the pH change is measured in terms of buffer index known as beta. Buffer index beta of a buffer solution is defined as, it is the differential ratio. It is a differential ratio, you can see dB by dpH. So, it is a differential ratio of what? It is an increment in adding strong base or strong acid to variation in pH. So, the expression is beta equals dB into d of pH. Here B stands for the small increments in strong base or acid whatever is added, and dpH stands for the change in pH. So, how much alkali you are adding and what is the change in pH? If you are adding an acid, what is the amount of acid added divided by the change in pH. And here one more point to be noted is that the concentration is expressed in moles per kg of the solvent. That should be the concentration we have to represent for both acid or a base that which is added. Now, we have to see how the buffer shows or resists the pH change by some sort of mechanism. Let us go into detail of that. First, I am going to consider an acid buffer, which is a mixture of weak acid. For example, I am going to take a weak acid as acetic acid and its salt, that will be CH3COO. You cannot put ammonium, it should come from a strong base. So, I am putting it as Na, or you can put it as potassium, which is from potassium hydroxide, all those things. Now, weak acid, it does not dissociate much. So, I am going to neglect its dissociation, while this salt which is coming from a strong base will surely dissociate to form CH3COO minus and Na plus ions. Okay. So, when we take a solution, what are the ions present in it? It will have acetate ions, sodium ions. In addition to that, undissociated sodium acetate and acetic acid will be present in the mixture. Now, suppose I am going to add an acid H3O plus. What happens here is H3O plus will react with, this is acidic. So, that will be going towards something which is basic in nature. So, this is the conjugate base formed from that. Okay. Or you just call it as this is basic in nature, that would be better. Just say this is a base, right. It is capable of accepting a proton. So, that is a base. Now, when I add an acid which contains hydronium ions will come and combine with the CH3COO ion, which is the base, leading to the formation of CH3COH and water. So, what happens whenever you add an acid, the acid hydronium ions that will not come in excess, that combines with the acetate ion and gets converted into acetic acid, which is only feebly ionized. So, the solution will not feel any excess of H plus ions or H3O plus ions in it. So, that is being removed from the system. So, the pH remains constant. Now, suppose if I am adding an alkali, that is OH minus ions, excess of OH minus ions will come to the solution, and this OH minus ion, here we have an acid here. So, that will combine with that acid CH3 COOH to give acetate ion and water. So, the OH minus ions are removed from the system. So, you do not have an increase in OH minus ion, and therefore, even if you add strong acids, there will not be any change in pH. In the case of acid also, the hydronium ions are removed, and therefore, there will not be any change in pH. And this is how a mixture of weak acid and its salt, that is a buffer, resists its pH change, and this is known as mechanism of buffer action of weak acid and its salt. Now, let us go for the alkaline buffer or basic buffer, where we have a weak base, let it be ammonium hydroxide, and its salt with a strong acid. So, I have to take ammonium chloride. And this ammonium chloride can ionize as NH4 plus Cl minus. So, there will be two ions, ammonium ions and chloride ions, as well as undissociated ammonium chloride and also the weak base ammonium hydroxide in the medium. Now, here again if I am going to add acid, there will be an excess of H3O plus ions coming from acid, and this will go to the base. Here we have ammonium hydroxide, this goes to the base ammonium hydroxide and get converted into NH4 plus OH is taken up by this, we will have H2O, 2H2O. So, again it is being removed. There is no excess of H3O plus ions, and therefore, the pH does not change. Now, suppose we add an alkali or a base. Here we have an acid. What is that? NH4 plus. This is acidic in nature because it can donate a proton. So, that will combine with NH4 plus and gets converted into ammonium hydroxide, which is only feebly ionized, and therefore, the excess of OH minus ions is also not felt in the solution. Either the addition of H3O plus ions or OH minus ions are not felt in the solution, or you can say that the pH does not change. So, this is the buffer action in the case of an alkaline or basic buffer. Now, there is an additional one, it is a buffer action of a salt of weak acid and weak base. So, the acid should be weak and base should be weak. So, I can put it as CH3 COO NH4. Okay. Now, this gets ionized as CH3 COO minus plus NH4 plus, not to a greater extent, but to a smaller extent. Now, if I add an acid, the acid will combine with the basic part, that is CH3COO minus, and converts that into CH3COOH plus water. So, you will not get any excess of hydronium ions in solution. Suppose I am adding an OH minus ion from an alkali, that is, if you add an alkali, it combines with ammonium ions and gets converted into ammonium hydroxide. Again, there will not be an excess of OH minus ions. So, even salts of weak acid and weak base can also act as buffers. Next, we have to find out what will be the pH of a buffer. I told you, if I take an equimolar mixture, it gives a certain pH. If the concentration of the acid and its salt or base and its salt are changed, you have a different pH. So, how will you determine the pH of a buffer? For that, we have an expression known as Henderson's equation, or it is also known as Henderson-Hasselbalch equation. Okay. Now, what we are going to do is, we are going to take an acidic buffer. Acidic buffer means it has got a weak acid Ha and its salt from a strong base. Okay. So, we will consider the dissociation of the weak acid, because acid is weak. It reacts with water to give H3O plus ions and A minus ions. Now, for this I can put it as Ka. To make it simple, I am going to exclude this water, because that is present in excess. So, the equation takes the form H3O plus into concentration of A minus divided by concentration of Ha. Hope it is clear. Now, here just like any other acid, Ha has been dissociated into its ions, and I have applied the equilibrium constant rule, where we have an expression for dissociation constant for that weak acid Ka. Okay. Now, we are supposed to find out the pH, and pH means, what is pH? pH means it is the negative logarithm of H3O plus ions. Concentration of H3O plus. Now, here we have H3O plus ions. So, let us make this equation in the form like H3O plus ions will be equal to Ka on that side, denominator goes to numerator. So, concentration of Ha in the numerator divided by A minus. Okay. To convert it into pH, I am going to take negative logarithms on both sides. So, this becomes negative logarithm of, I will put it negative log of H3O plus, which will be pH, and that is equal to negative logarithm of the whole term Ka into concentration of Ha divided by concentration of A minus. Okay. Now, taking logarithms, it becomes, this becomes pH is equal to, here I am going to take the negative logarithm inside the bracket. So, minus of log Ka. Okay. The next term I am keeping it as such, minus of log concentration of Ha divided by concentration of A minus. Okay. Now, this can be written as pKa, and here this minus can be made into a plus provided I just revert this fraction. So, it becomes plus log concentration of A minus divided by concentration of Ha. Okay. Now, here this is the expression for pH, in which A minus stands for the ion A minus, and that comes from the salt. Because it is a weak acid, the ionization will be very little, and therefore, the A minus concentration, that is in the electrolytic solution, will be from its salt rather than from that weak acid. So, the concentration of A minus can be considered as the concentration of the salt. Okay. And Ha, of course, that is the concentration of the acid, weak acid. This will be concentration of the acid. In that case, the expression can be written as pH is equal to pKa plus, instead of A minus, I can put it as concentration of the salt divided by concentration of the acid. And this expression is known as Henderson's equation. Here you can see that pKa is the dissociation constant of the acid, while the other two factors are concentration of the salt and acid. The proportion decides. Once you fix the weak acid, the pH is determined by the concentration of the salt and the weak acid taken. So, adjusting that, you can control or you can have a definite pH which you require. Now, let us go for a basic buffer. Basic buffer is a buffer which has a weak base and a salt Ba. Here, though the base is weak, acid should be strong. Okay. So, this is our expression for dissociation of a weak base. Now, in the former case, what we did was we just wrote the dissociation equation, and from that we wrote Ka, that is for a weak acid, or in this case we have weak base, base is weak, and therefore, I have written the expression for dissociation of the weak base. Note that point. Now, from this I can write it as Kb is equal to concentration of B plus into concentration of OH minus whole divided by concentration of BOH. Now, from this you should note that there is no hydronium ion. What we are going to have is an hydroxyl ion. So, if I get a hydroxyl ion concentration, you can get only POH, and getting POH means we can convert that into pH terms, provided subtract the POH from 14 will give you the pH. So, that is the way we are going to approach this. Now, so from this I am going to find out the concentration of OH minus, because that is the only way we can do it, will be equal to Kb into concentration of BOH divided by concentration of B plus. Okay. Now, I am going to take the negative logarithm, that is negative log of OH minus can be taken as POH, negative logarithm of Kb can be taken as pKb. I am writing it in single step because similar to the same derivation which we have done just for an acid. Now, plus here I am putting it together, not plus, that will be minus, negative logarithm minus log of concentration of BOH whole divided by concentration of B plus. To remove this negative sign, I am going to invert this fraction and you will get the expression as POH is equal to PKB plus, just see here we were having the base on the top and B plus at the denominator, you just revert it, you have B plus at the top and BOH that is of the base. And B plus, as we all know, it comes from the salt, because here we will be having very little B plus ions from the weak base and most of the ions B plus is coming from the salt. So, that gives the concentration of the salt over here and this will be the concentration of the base, and that has been reversed, you get the Henderson's equation. Now, using Henderson's equation, we derived an expression for POH and pH can be found out by subtracting POH from 14. Next, let us see what are the applications. To calculate the pH of the buffer solution by preparing known quantities of weak acid and its salt or weak base and its salt, it can be done by Henderson's equation, and also you can calculate the quantities required to prepare a buffer solution of a definite pH. Now, let us see what are the applications of the buffer. In analytical chemistry, we use acetic acid sodium acetate buffer for elimination of phosphate radical from inorganic qualitative analysis. You add ammonium chloride and ammonium hydroxide as a buffer in complexometric titrations using EDTA, where we are going to titrate it with zinc or magnesium or calcium like that. Here we are going to take a buffer so that there is no change in the pH during the titration. Now, again for alcoholic fermentation, for tanning of leather and all such processes, we require a constant pH and for that also we apply buffer solutions. The citric acid sodium citrate solutions, they are used as buffers for sterilizing penicillin preparation. It is an antibiotic. Then milk of magnesia, it is used as an antacid. So, for many preparations we use buffers for their stabilization and sterilization processes. Many of the biological reactions taking place within animal systems require a constant pH condition and that is made possible by a buffer carbonic acid and a bicarbonate mixture. So, it has wide applications for buffers. Next, we will go for a problem based on Henderson's equation. Now, here the problem goes like that: a buffer solution contains 0.40 mole of acetic acid and 0.20 mole of sodium acetate. So, it is a mixture of acetic acid and sodium acetate. So, what is that? It is an acidic buffer. Okay. State. Calculate the pH of the solution. Ka of the acid is given. Ka of the acid is given because it is a weak acid and its salt. Now, according to Henderson's equation, pH is equal to pKa plus log of salt by concentration of acid. You can directly apply that because all these values are given here. The only difference is they do not give the pKa value, they give you the Ka value. So, I have to modify this equation as negative log of Ka plus log of concentration of the salt divided by concentration of the acid. Okay. So, both are given here. See, acetic acid, it is concentration of acetic acid is equal to 0.040 mole and that of sodium acetate .20 molar solution. Ka is given, you can calculate it as negative log of Ka. What is the value of Ka? 1.75 into 10 to the power minus 5 plus log of concentration of the salt, that is acetic acid 0.20 divided by 0.040. Now, solving that using a scientific calculator, you will get the answer as 4.4559 as the pH. So, that is for an acid. If it is a base, you will get POH instead of pH, subtract that from 14 and you can find out the pH. So, in a similar way, the expression is almost the same. Now, let us conclude. In this session, we have been seeing buffer solutions and those solutions resist the change in pH on addition of appreciable amounts of strong acid or a strong base. So, it is very convenient if you want a reaction to occur at a certain pH and that reaction involves addition of acids or bases. Better conduct it in the presence of a buffer solution, so that the pH is not altered. Next is the buffer index. Buffer index is the capacity of a buffer to resist the pH change. If the buffer index is greater, that means it can resist pH for a greater amount of added, it can be acid or base. Mechanism of buffer action we have already seen. We have seen buffers of two category, that is alkaline buffers and acidic buffer. They both have their own way of neutralizing the H plus ions or H3O plus ions added from an acid or OH minus ions from a base. And finally, we landed up with the derivation of Henderson's equation for determining the pH of a buffer. Thank you.